Hi, this is Caroline and welcome to my video log for my mini project. I'm so excited to get started and build a spaceship. Yep. What do you mean error? I need some coffee. I'm sure I wrote down the formula correctly. I can do this, you can do this, you can do this, you can do this. A spaceship! What? Why are there two spaceships? You will work. This is not the error message you're looking for. And now it's gone. Work. Why won't you work? Hi, I'm Caroline. They gave me something to make me feel better. I feel much better about my program now. You can feel better too, in just 6 easy steps. So the first thing we're going to do is a bit of a stock take as to what's in the program template we've been provided with. So let's check it out. So here I am inside the project template, and there's a lot of strange text floating about. Once you get a program that starts to get a bit more complicated, what you really need is some kind of documentation to help you keep track of what's going on. So I'm going to start by organising this program template in a way that will help it make more sense to me. So the first thing I'm going to do is I'm going to look for all the classes in the program template, and they all have this syntax. There's 3 of them: an image info class, a ship class, and a sprite class. So next thing I'm going to do is I'm going to do a bit of categorization and organisation of the things I found. As well as the classes in my program, I'm looking for objects. Objects have this syntax: a variable followed by an equal sign, or a variable dot method and parentheses. I found a lot of objects in this program template, and for each of them, I'm going to arrange them under the correct class. This will help me get an idea of exactly what I'm dealing with in the program. Alright, so that's great, but what are all these objects here over on the right? They are objects, but they don't seem to belong to any of the classes. Well, these are actually code sculptor objects. Okay, so the other thing you should notice about these objects is that they're not actually objects, what I've got on the table here, they're just labels. And the labels direct the computer to go to an object. We have a ship object, we have some sprite objects, and we have image info objects. So that's the first 2 steps done. We've done a stock take of what's in our program template, and we've arranged it or organised it into classes. Now you might also want to sort all these code sculptor objects into something a bit more meaningful. I've divided them up into image URLs, sound URLs, global variables, and simple GUI objects. Now I know what you're thinking. You're thinking, this crazy lady wants me to try and troubleshoot my program by labelling fruit. Well, I have to say, it sure beats banging my head against the desk, but no, of course you don't have to label fruit, you can just do it in a word processor document. That's how I actually did it, but I thought that might be a bit boring for a video. So we've got our documentation organised. Now we're up to step 3. We have to think about how some of these objects are used to build other objects. And to do that, we first need to get a bit of an idea of what the different objects are. The image info objects hold key coordinates to display an image. The ship object is a user-controlled arcade-style spaceship. And finally, we have the sprite. A sprite is a 2-dimensional object displayed in a scene to give a visual illusion that there's a real object or character moving about there. So what exactly is the difference between a sprite object and a ship object? Firstly, let's take a closer look at a sprite. Here's a scene, and here's a sprite. It's just a ball, or a circle, because it's a 2-dimensional object, but it gives the illusion of being a ball. Now, in addition to being a 2-dimensional object, a sprite has other characteristics. It has a position in the scene, an X value and a Y value. It can also have other characteristics such as a lifespan, which tells it when to disappear. By contrast, our ship is a user-controlled object. It displays in the screen like a sprite, but it does lots of other things as well. We can control it, we can send it in different directions, we can accelerate it, and it can shoot missiles. So let's think about how we could build a ship from the objects we already have. We could write all the code for displaying on the screen inside the ship object, but since we already have a sprite that does that, why don't we use the sprite as a component of the ship? And the sprite itself, we can build that up out of the image URL and the key coordinates in an image info object. And there's also a sound URL to go in the sprite. So we know the sprite will have certain attributes. It will have a position on the screen, it'll have a lifespan, and we know that the ship image is going to point to a particular URL, and if we go to that URL we can see an image that looks a bit like this. And we know that the ship object is going to have all the logic for interpreting how the user presses the keys and telling the ship what to do in response. Now here's a puzzle. The image of the ship has two images, one with thrusters and one without. The ship info object points to the first image, the one without thrusters. Now this means we're going to need a second image info object to actually point to the image of the ship with thrusters for the occasions when we want to use that image in the sprite sheet. Which means that somewhere in this program we're going to have some logic for selecting which image is displayed. Now where is the best place to put that logic? If we put it in a sprite, we want to be confident that it's the kind of thing that all sprites are going to need. So is a rock sprite going to need to know whether the thrusters are on or off? Is a missile sprite going to need to know this? I don't think so. So what if we move the logic over here and put it in the ship? Arcade spaceship's going to need to know whether to turn the thrusters on or off. Pretty obviously yes, and if we decide to create multiple ships, then they'll probably also need to control their thrusters. So let's create a second sprite. We might call it ship_thrust_sprite. And this one can have the ship thrust info and the ship thrust sound, and both sprites can refer to the same image URL. And this brings us to step 4, encapsulation. And the good news is we just did it. It just means asking, do I want all objects of this kind to do this particular thing? Because what we want to avoid is needing to open up the object after we've already designed it and finalised that design to get it to do new things. In particular, we don't want it to have to do new things for just one object. We want it to be essentially a black box. So here we can see how the objects relate to each other. And this takes us to step 5, which is to diagram methods from object to object to better understand what they do. Generally, the frame's going to call on the ship's going to call on one of the sprites, and the sprites have already been created with a ship image and ship info and sound. We're going to look at the ship's draw method, so we're going to need to add in a frame object here because that's the object that calls it. So the ship's draw method is called, and the ship thinks, are my thrusters on or off? Let's see, they're off. So I'm going to call ship sprite, not ship thrust sprite, and I'm going to say, draw yourself. And ship sprite says, yay, I get to draw myself, and tells the frame to draw it wherever its current position is. Let's do the ship's update method. The frame's going to call it. The ship is going to do all the calculations to work out where it is. And remember, the frame's calling this every 60th of a second. So it's working out where the ship moves with all the velocity and acceleration calculations. It's then calling the sprite to update itself to the new position that the ship gives it. So hopefully now you have a better idea of how your program works and how it's supposed to work. Now step 6 is just something a little bit different, but also something you might get stuck on. It's understanding the maths of acceleration and friction. Here I have an object, a rock, and the little white rectangle above it represents that it has 1 unit of velocity. So it's travelling at a constant speed of 1. And each turn, it advances 1 unit. Now I'm going to add in 1 unit of acceleration. And the way acceleration works is that it adds 1 unit to the velocity each turn. So our rock's velocity is going to increase by 1 every turn, which means that it moves 1 more space than it did last time every turn. And we can see, for example, if we had an acceleration of 2, the velocity would increase by 2 every turn, and our rock gets further in the same amount of time. Now let's get tricky and add in some friction. Friction is a force in the opposite direction from acceleration, but unlike our acceleration, it's not going to be constant. It's going to change depending on what the velocity is. And you can imagine this as though when an object gets faster, it has to push harder through the air, or in our case, debris. I've given our friction a factor of 0.5, so it's going to reduce the velocity by half every turn. In one turn, our rock moves forward 1 unit, it gains 2 units of acceleration, but its former velocity is decreased by half. So its new velocity is 2.5. So let me take the current velocity, halve it for friction, and add 2 units for acceleration, and so on. And what you'll notice is that the velocity actually starts to level off as it approaches 4. This is because with a friction coefficient of 0.5, it's halving each time. So acceleration is managing to add 2 units. The velocity halves that. Even when it reaches 4, it can only go back to 2 units. So it's approaching 4 and leveling off. From this exercise, we can figure out the rule. Acceleration adds the same amount to the velocity each turn. So in our example, it's the velocity equals itself plus 2. Friction multiplies the velocity by a fraction and then takes that away from the existing velocity. Each turn, velocity plus equals acceleration and velocity minus equals the velocity times by the friction coefficient, which is a fractional number. Just to recap, these are the 6 steps or tips. Firstly, stocktake the program template. Find all the objects by looking for this syntax. Then organise what you've figured out. Then you want to think about building objects from other objects. You want to think about encapsulation. Will all of this kind of object need to do this particular task? And can I achieve my goal without looking inside the object? Then you might want to diagram your methods, showing how they move from object to object to better understand what they do. And finally, if the maths is freaking you out, visualise it with concrete examples and then extrapolate from those examples to what the abstract maths must be.